Let's talk about the careful definition of the limit of a function. So that's a function, let's say f maybe, although we might use different names eventually, that takes a real number as an input and spits out a real number. And maybe not all real numbers are in the domain or something like that, but basically something has real inputs and real outputs. So this is different from a limit of a sequence, which I was talking about in my limit of a sequence videos, which you really should watch before this because I'm going to assume that that you've seen those. So in other words, the notation that we have is the limit as x goes to a. This is going to be some sort of constant value, usually fixed value, of f of x is some number L. And what does that mean precisely? Well, we do want a picture. We don't want to just be purely formal. And I'll start with x and y, although I'm going to change to a concrete example as soon as I reasonably can, where the variables are going to be a little different. So we have some function, and I'm interested in the values of f of x when x is near a. And so I'm going to imagine putting in something near a, so some other x value near a, and I want to assert, let's see, I want to assert that f of x when x is near a is going to be near the value L. So our first approximation would be when x is near, and really very near, but we're going to really have to quantify that in the same way we did with the sequences. When x is very near a, f of x is very near L. Okay. And we're going to make that precise in the somewhat surprising way we did with sequences, but it's going to be very analogous to that. So we need to quantify very near in both cases, and be more specific about that. But one thing I want to address right away is a lot of times people are like, why would I even bother? Why don't I just plug in f of a and see if it's equal to L? Isn't that just a much simpler version of the question? Okay. Well, so what we're going to do, what we're going to be in the situation of, most of the time when this is useful, and the crucial times when it's useful for calculus, to create the two big notions of calculus, derivatives and integrals, we're going to be looking at a function that we can't actually make sense of the formula for when x is equal to the target value. So that's usually denoted by a little open circle here. And it may seem very artificial, like, well, you just deleted a point. Just put it back, and you'll be done. Put it back and plug it in. But we'll see that there's cases when you have a formula for a function that really does refuse to give an answer in exactly the case you would like it to give an answer, and you have to approach that value a instead of just plugging it in. It's a real thing, and I think most calculus books don't foreground that quite in the right way. Okay, so we're not going to be able to just say, oh, just plug in a and see if it's equal to L. Kind of like with sequences, we couldn't just say we have a sub 1, a sub 2, a sub 3, a sub 4. We can't plug in a sub infinity. Infinity isn't a number. There was no infinitieth term in the sequence. There was no such thing as plugging in the infinitieth thing and seeing if it's exactly equal to the limit. So there it's a little easier to see why you can't do that. Here, it's going to be good to look at an example. But before we go to an example, we can get a better sense of how this is like the sequence case, and how we could make it more like the precise version of the sequence case. So the key thing there was something that was a little backwards for most people's intuition, which is you look at the very near on the output side first. You think about who's my customer, how accurate do they need this output to be, and you put a little error band around there. And so I'm going to make it pretty big visually, although usually you want to think of it as pretty small. You're going to say, my customer today, they're willing to accept an output that isn't exactly equal to L. And like I said, there's a lot of cases where you're not going to get exactly equal to L coming out of whatever formula you're using. But they're willing to accept any answer between L plus epsilon and L minus epsilon. And different customers have different epsilons. The carpenter has an epsilon that's maybe a 10th or a 100th, and the rocket scientist has like 10 to the minus 10 or something like that. Okay? Very like the sequence situation. Now, instead of with the sequences, it was, is there some waiting time after which I'm guaranteed to be in there? It's, is there some sort of boundary, is there some sort of bound on the input that I can put in? So this sort of happens first, and then based on how accurate the output needs to be, how close to L that needs to be, I say, is there some sort of wiggle room in the input so that no matter what x I put in near A, in that wiggle room, I will get into the right boundary. So let's see. So for here, it looks like, maybe like here, this is going to work. Notice if I make sure that I'm always, it's not very symmetrical. It's usually, you usually want it to be symmetrical. It's much simpler. That's how the definition usually works. As long as I'm within this much, left or right, of A, it looks like all the values, except at A, and we'll reiterate that in a second, all the values of this function, there's all these heights in here and in here, are well within the band that we have determined satisfies this particular customer. So this gets another Greek letter. This, the wiggle room plus or minus here is called delta. And so this is x would be equal to a minus delta, and this would be a plus delta. Okay, and so our next approximation is that when x is between our target input plus delta and our target input minus delta, the output is within that error tolerance of the desired output. Now, there's one subtle point. As I said, the most interesting case for this with calculus is when there isn't even a value defined for f. So, in fact, f might not even be defined on all of R. It's really common that it just drops out here, and we don't have a really good way to actually evaluate the function here. And again, if that seems weird, you'll see. We'll show you examples. And so, to be technical, I don't really want to force myself to evaluate x at the one place where I know it doesn't work. So we could say x not equal to a. And there's going to be cases where it's totally fine to plug in x equals a, and you better get something close to L when you do that too. In fact, you better get L. But really, the most interesting cases are where you have this kind of little open circle as dropout. Okay, so this is really the key, and I just have to make sure I do the quantifiers correctly and the order of the logic, and remind people that the epsilon really gets chosen first. And first you have to figure out how accurate am I requiring the output to be, and then I choose a delta. And before I write that down in sort of precise logical language, let me reiterate what was so important and true about the sequence case. It's that this isn't just working for one epsilon. That's not particularly interesting, and it's not what the mathematician's job is. If maybe the mathematician who only works with carpenters says, you know what, for me epsilon equals 1/100th, 0.01, will always work, and that's the only accuracy they ever want. You could have that kind of definition. But the point of this, the definition of a limit in mathematics, which is supposed to serve every possible conceivable customer, to say that this limit is equal to L means that no matter how finicky we get an epsilon, then we can make sure that those values are going to be within that band. Now, you're not going to do that unless you change delta in accordance with the epsilon. So, just one more variation on the picture. If I look at the much more finicky customer, who has a much smaller epsilon, now notice if I use the same delta, and I let my x's go between a and a minus delta, I'm going to get these values that are not inside that narrower band. So I'm going to have to change delta to accommodate that. Erase a bunch of this stuff. Okay. So the delta has to be chosen based on the epsilon. And that precise relationship can be part of the finicky, weird algebraic nature of the actual proofs you sometimes do, just like choosing the big N for the sequence case involve things like let's take 1 over epsilon, or let's take the log base 2 of epsilon, or log base 10 of epsilon, things like that. So let's write down precisely what it means. I feel bad about not giving the example yet, but I want to go ahead and write down the definition. Okay, so here's the definition. Okay. it says that for every possible epsilon greater than 0, so that's every customer that you could serve, and of course it's greater than 0, you never require exact precision because this is all about limits and approaching and nearness, okay? There is a delta that's also greater than 0. So this is the error bound you're trying to satisfy on the output. This is the wiggle room that you can allow on the input to achieve that, such that, okay. Now, the whole point is that this is all about x's and f of x's, okay, such that for every, one more quantifier, it's a 3 quantifier definition, for every x with x in between a plus delta and a minus delta, and where you don't worry about what happens right at a, largely because the interesting examples just wouldn't work there, okay, we have the output is within the desired tolerance of the limit. Okay. Again, this is something that strikes many people as a very complicated definition. Part of it is because we've swept under the rug definitions of concepts in like pre-calculus that are almost as complicated. Actually, some things that are more complicated, like how do you calculate the sine of 17 degrees exactly, for example. It's just this is one of the first times we actually trot it out, because there's enough subtleties that you can get yourself mixed up in without this careful definition that it's often worth it at this point to be careful about it. Remember, though, that I want you to not think this is an overly complicated definition, because it really is capturing some very practical considerations. Given a certain error tolerance, depending on the customer, is there some wiggle room so that when x is near a, this just says x is near a with a precise sense of near, meaning plus or minus delta, then the outputs are near L. It isn't any more complicated than it really has to be, I would say. Okay, so pretty long video so far, but we got to the actual definition. And then I'm going to, in the next one, I will look at an example that comes straight from calculus, from a derivative, and in fact from a physics kind of derivative, a velocity, that illustrates how this could get used, how we could prove it, and this issue of the x not equal to a. So, stay tuned.